Primero empiezo por agradecer a Karen Antorbesa y Francesco Milano, que son los directores del Camaco, el taller de materiales y construcción que está en Chela, en el Centro Intermediático Latinoamericano, no sé si lo conocen, que en realidad gracias a ellos Andrea y Marco pudieron venir a Buenos Aires y entonces nosotros conseguimos traerlos acá a FADU, así que es el primer agradecimiento para ellos. Y en segundo lugar les presento a Marco Palma y a Andrea Graziano, que son los que van a dar la conferencia hoy. Ellos pertenecen al DigiFab Turing de Torino y al colectivo de investigación CODEIT. Les aconsejo buscarlos a los dos en internet. Tienen obviamente su página, su Facebook, y todo el tiempo están subiendo cosas realmente muy interesantes. Sobre todo van a ver que trabajan mucho, obviamente, en la relación entre fabricación digital y exploración, investigación, nuevos materiales, mucho sobre todo con robótica, que es una cosa que está empezando de alguna manera, digo, se sale de los estándares normales de las impresoras digitales o el corte láser, ese tipo de cosas. Así que van a ver cosas realmente interesantes y novedosas. ¿Sí? No sé si quieres agregar algo, Francesco, respecto al trabajo de ellos, si no, igual se van a presentar a sí mismos, me imagino. Bueno, Andrea.
Thank you very much. Good evening to everyone. Thank you for inviting us. I want to thank you, obviously, Francesco and Karen, for the invitation for the workshop, and the FADU Università for inviting us as a lecturer. In the evening, the presentation will be split in two parts. The first part will be more sort of theoretical one in order to create the framework in order to understand better the second part that will be related to the last 2 years of research that we did in our DigiFab Turing lab. As Rodrigo told you, I'm part of CODEIT. CODEIT is a sort of Italian hub about computational design, and I want to describe it as an hub because it's just connecting people that want to use computation as a design medium in very different disciplines. So the common interest is to use the computation as a medium in order to describe. We are actually a huge group. Many of us are working all around the world, spread in different offices, but we are working on some specific research together. I want to start the theoretical framework part of the lecture with a quote from Kevin Kelly. It's a quote from one of his latest book, What Technology Wants. It's not that new, but is a 4 years old book. And in that quote, Kevin Kelly, if you don't know him, maybe you can just check on Google, but is one of the, I think, the most interesting point of view about the use of technology in the last years. So in this book, he's saying, okay, about 10,000 years ago, humans passed the tipping point where our ability to modify the biosphere exceeded the planet's ability to modify us. That threshold was the beginning of the technium. Then we are at the second tipping point where the technium's ability to alter us exceeds our ability to alter the technium. So we are living in a new age, a new era, where the technology is changing us more than our ability to change the technology itself. I'm pretty sure you are quite used to those images. My parents and my wife as well are criticizing me for the intense use of technology every day I'm doing. But this is something not really new. It always happened. Since the technology is a way to drive information to our attention, technology is catching us all the time. So this is something that always happened since the very early stage. And it happens so many times that at a specific point in the history, the technology started to change in our mind until it reached different levels. In first, the technology is envisioned by the people that are studying the technology itself, that they are developing the technology. Then, those prototypes start to be operational. So, they start to be available for some person that are testing it. Then, there is another step, the application of the technology. So, the technology is applied. Then, if it's successful, it could be accepted. So people starting to use the technology in a very wide way. It's widespread. Then, as you really well know with your smartphones and so on, it starts to be vital. If you're losing your smartphone, you're losing half of your long-term memory in some way. Then it started to be invisible. You don't care about the technology that is surrounding you because you're so used to that that you don't care anymore. And then it starts to be naturalized. In some way, I could challenge you to go home tonight and look at everything you can see around you and think if it's not a technology in itself. Also the park, also the green, also everything around you is technology. Agriculture is technology. But we don't consider technology anymore because it's old. We are used to that. We didn't born with the rise of the agriculture. So it's something that we could consider naturalized. Then, in 2014, I saw a TED Talk, probably the most of you really well know what is a TED Talk, by these guys, Joy Hito. In 2014, he was chaired at MIT as a Media Lab director. And during this TED Talk, he changed the approach that the MIT Media Lab has before. Before of that time, the MIT was driven by Nicolas Negroponte. And when he started the new era at MIT, he said something that was really interesting. Every project has to be deployed or the project will die. Everything has to be in some way prototype or the project is not good enough to survive in the lab. So basically, you have to push the limit of the project. It hasn't to be just a speculative or just a demo. The prototype is something really different from a demo. It has to be something that is operational, so it works. It's the last step before the industrialization of a product. And at the same time, in Code 8, we were discussing how to filter our research project in our group, because we weren't that much at the time, and at the time we need a filter to filter the project that we were interested to. And basically, we started to adopt the same criteria. So we will push further just the project that could be prototype. So the prototyping phase is something that really changes your attitude to the design project, because it needs to start to challenge in some way yourself about the knowledge into materials, the knowledge into the tools that you want to use in order to prototype, and the knowledge about the code in order to transfer your ideas into the machine that you are using to inform the matter. During the same lecture, Joy Hito, the director of the MIT Media Lab, showed this diagram that was really interesting. and is still very interesting to us, for us. Basically, he was saying that the future of design will be a sort of intersection of those 4 disciplines. The computational design in first, and we were mostly into that. Then additive manufacturing, and that was the time where we started to research about additive manufacturing technologies and techniques. Then material engineering and synthetic biology. So those 4 different knowledge fields will be the common ground for the future of the design. So I want to start to show to you some slides about what's going on around us and which is our ability that we developed in the last 10, 20 years in order to manipulate the matter, the materials as well. So if we don't know which is our ability, the technologies that are available in order to deal with the materials, we can't really understand what we could do with the material itself. And as architect and as designer, this is really important. If you don't know which is the framework where you are working, it's very hard to define your projects. So the first slide, obviously, I think it's very common to every one of you, is a 3D printer. And Neri Oxman, some years ago, was talking about 3D printing that way. As the Gutenberg revolution allows anyone to print books, democratizing information, 3D printing is revolutioning the way we do fabrication. In some way, we can all make. But our point of view as Code 8 about 3D printing is slightly different, maybe, from the common idea of 3D printing. 3D printing is not just to give some shape to some materials, but it's a way to add several layers of information during the fabrication process. Why? If you think the standard 3D printer, in the standard 3D printer you can define how and when you release the material, which is the position of the release of the material. So basically you have one layer of information that is about the position of the material, but in this image you can see that there are some other information about the material. Basically there is another layer of information that it's about the color. So for each voxel, a voxel is a pixel in 3D space, you can define not just the position of the material, but also the color of the material. So it's another layer of information. Then, always in the same object, the matter could change from very stiff material to very soft one. So basically, the change of color is related also to the change of the stiffness of the material. So you have another layer of information, and you can manage the material itself going from very stiff one to a soft one. If those are the rules that you can use in order to create your design, you can understand that you have 3 different layers of information that you can play with in order to create something. And some architects, already some years ago, started to play with those kind of technologies and these kind of opportunities that those kind of technology provide to us. This is a very famous chair from the Zadig Architect Studio, and basically the change of color is related to the change of density and stiffness of the material itself. So the blue one, the blue voxel, let's say, are related to the most stiff material, and the position of these blue dots are related to some topological optimization processes. So basically, you can define where you need more material and the rigidity of the material that you need in the same object. So you put the rigid material just where you need it, and the other parts of the chair are really more light in some way. So you start to adopt the material just where you need it. Then we started to use the material in a very different way. This is a sort of mechanism, a mechanical part, but not in metal parts. It's made by some rubber, but the topology of the deposition, so how you distribute the material during the deposition, will define how the final object will work, assigning some forces to some parts. So it's a sort of door handle that it really works really well, just driven by the topology of the material. Then we started to see something really new. This is so-called 4D printing. The 4D printing is not just to print something that could move. It's something really different. It's a 3D printed object with another layer of information that's about how the object behaves in different environmental conditions. For this object that was 3D printed again at the self-assembly lab at the MIT Media Lab by Skylar Tibbits, there are different layers of material in this cube, and one layer is a sort of plastic, and another layer could react when you put this kind of material in water. So basically, this second layer started to shrink into the water. And so if you know that you have this double layer, the material, when it's put into water, starts to shrink itself and will define the shape of the object in different conditions. So 4D printing is about to change the properties of the material in different conditions. But our ability to manipulate the materials could really reach more small properties. That's a very old image. It's from 2012, and it's about nanoprinting. So our ability to define the material properties is going to be at the nanoscale. This is a still object, but this is not a still object. Those are two nano mechanisms that could be printed. So you can imagine to have some materials that at the nano level could embed those nano mechanisms. Can you imagine some fabric on your jacket with those nano mechanisms, and when you move your arms, that scale of movements provoke a really big energy at the nano scale. So you can start to think about storing energy, to make storage of the energy in the material itself. And then our ability could reach even further points. This is a IBM video. It's called A Boy and His Atoms. Basically, the video is a video recording of some atoms. So our ability to define the material is going to be at that level. Like this one, this is a molecular 3D printer. So basically, you can't print atoms one by one, defining the final material. You can have, if you can have all the ingredients made of atoms, you can define which is the final material that you have. So those are the technologies that are available actually, obviously not in architecture, not in design, still not, but it's going to happen. This is, for instance, a material that could change from solid to liquid by the atoms connection, driven by some magnetic forces. So basically, we can define some material that will change the state, the solid state to liquid state, by some magnetic properties. Then, our ability to manage different materials started to jump in a completely different field. That is the bio field. So 10 years ago, this was one of the first company, EnvisionTech, that put on the market this 3D bioprinter. Basically, it was a very expensive one. It was about to create and to print some bones part or soft tissue or drugs or bio skin in order to replace the skin in injured persons. Anyway, this 3D printer started to show that not just the common materials could be organized with this kind of processes, additive manufacturing processes, but also the biomaterials. And in a couple of years, some doctors, this image is taken from a research made by the Dr. Anthony Atala, and was about to start to 3D print organs, basically. You can see a fully functional kidney on the left, to the top left, then some scaffold for ears, new ears, and some finger bones. So we started to jump in a completely different field where we could start to imagine to use biomaterials. This is an image coming from the Wyss Institute for Biology, and it's about to use some composite biomaterials that change their properties when those structures are put or placed in water. So the material itself started to react and change the shape in itself. This is another very famous project from the MIT Media Lab. It's called Biologic. It's a sort of fabric, a fabric that reacts to the changing of temperature and moisture. So basically, it's made by some biocomposite. The name of the composite is natto. It's something that is inside the rice stalks, and is a material that changes the length of itself. So basically, it shrinks by the atmospheric moisture. So as a fabric, it's something that if you wear it, it changes the shape driven by your temperature and your level of moisture. Actually, it's exhibited in Linz. We were there 3 weeks ago, and we showed the functional prototypes of it. It's a very interesting material. But our ability to work also with biomaterials is going further, and this is a project called Stingray. Basically, it's a completely 3D printed object. The skin is made by a gold part, and the living part is made by rat cells. Basically, the rat cells were modified in the DNA code in order to react to some light stimulation. So as you can see in the very small images on the right, with the right amount of light, the 3D printed object started to move its own shape according to the light source. But if you think that all these kind of things are really far from you and are really expensive, this is a very, very old image from 2010. This is a DIY bioprinter made by the Barrio Curious lab in Sunnyvale. It's a project about to do a 3D bioprinter with $150. So it's a technology that you can download from Instructable. It's a very well-known website about DIY technology. And you can download and you can assembly on your own. And those are the first tests that they did in the lab, basically 3D printing some food for some glowing bacteria. So basically, if you're 3D printing the food position, the glowing bacteria obviously will reach the food, and this is the final result. But we are entering literally in a new era of design. And we have also to define and to understand which is our position as architect and designer into this kind of new framework. Since 15 years, at least, a lot of industry are trying, and in the last 10 years, they also figure out how to do that, to decode the DNA sequences. So basically, we are able actually to read the DNA code of every living being and to sequence the instruction inside of it. And our ability is not just in the reading process of the DNA, but also in the writing process of the DNA. If 10 years ago to write a string of DNA was really expensive, actually it's something really cheap. You can read the entire human genome with $100, and you can write with $1,000. So it's something really cheap, actually. And some institutes started to think about what it means to be able to read and write DNA. Basically, is a very powerful way to storage data. This is an image of Dr. Nick Goldman from the European Bioinformatics Institute, and it shows a very small pipe containing just 2 grams of DNA. In 2 grams of DNA, basically you can store the entire digital data we have on the internet now. It's insane, the amount of information that you can store in the DNA. You can do a backup of the entire digital data with very few grams of DNA. So this is something that we have to start to think how to use this kind of technology if we want, obviously. If you don't trust me and you think it's something really far, you go on Amazon and you can buy this sort of very small USB stick. It's a DNA reader. So basically you can place any kind of biomaterial inside of it and you start to decode the DNA string. Maybe you're not aware, but in 2010 happened something on the planet that never happens before. I consider this image of like something that my son has to study in the history books. The man that you see on the left, top left, is Craig Venter. He's the CEO of the Craig Venter Industries. Basically, in 2010, they did one thing that never happens on the planet. They took the most fundamental and easiest, let's say, bacteria we have on the planet. It's called the Mycoplasma, mycode, and it extracts the DNA from the scaffold of the bacteria. Then it completely discards the DNA itself and keep just the scaffold. Then on a computer, they program the new DNA, and they fit the new DNA inside the old scaffold. And after a few hours, the bacteria start to do two things that are the fundamentals of life: eat and reproduce. Those are the foundation of life. So basically, for the first time, we have a completely synthetic form of life on the planet, something that we code. It's very important. And since this experiment, a new scientific field started to arise. It's called synthetic biology, and basically it's the design and the construction of biological devices and systems. So actually we have the opportunity or the ability, or I don't know how to call it as an architect or designer, but we are able to start to think not just with still matter, but also with material that are biomaterials, and to think about it in terms of design. So as a computational designer, I was quite used to the top part of this image. Those are logic gates in order to define how some processes are working. So you can define if something is true, false, and all the set of relations you can define in a programming language. But on the other side, there are some biologists that are working with the second set of images you can see on the bottom part. Basically, they can do the same logic gates with molecules. So you can start to define how the biomaterials are working in order to produce some changings or some processes. And if you think is, again, something really far from you, this is a screenshot from my laptop. This is an app where you can start to take some samples of DNA strings from very different sort of bacteria. They are free. Those apps are free, and you can find around 1,000 on Google Play. You can start to take some strings and to play. I don't know how to say, to design, maybe, it's more, has more sense. But you can start to play with the DNA strings. And if you, maybe you can't read that, but on the top right, there is a button with the name pricing. So basically you can start to play with it and then to ask the price in order to print it. And in 3 days, I did it 2 years ago. In 3 days, you have the new strings of DNA inside the pipe. Obviously, I don't know what to do with it, but just to test the process. Keep in mind that just in the United States, the number of the bio garages where kids and very young people are playing with biology are more than 1,000. The bio garages in the United States. The FBI department has a new department just for that kind of things. So what we were doing on our laptop using the usual code, the 0 and 1, let's say, language, is happening also on the other side, using the molecules and the cells as hardware and the DNA as operative system. Keep in mind that the DNA is the operative system of nature, okay? So in those last 10 years, we are filling the bridge between those kind of languages. So actually, we are able to jump from one side to the other, from 0 and 1 to ATCZ, language. And obviously, I'm pretty sure every one of you is asking, okay, why I have to be interested to that? Why it's very important for my studies and so on. This is an image I took from the Skylar Tibbits website maybe 3 or 4 years ago. It was about to 3D print the longest chain as possible in a fixed size volume, okay? How can I fill with the most longest chain the space? It's called, has a very specific name, this process that I don't remember now because I can't read the slide. Sorry, I will check later. Anyway, you have to build an algorithm that is filling the space with a specific object. The same is happening in biology because the way the DNA works in order to read the sequence itself and start to trigger some specific function is defined by the way you fold the DNA. So folding the DNA is the way you define in which time every string will be activated. So folding the DNA is a very strategic way to define how a biomaterial is working. And as you can see, they are using exactly the same tools, exactly the same computational approach. So the computation is the bridge between something that is happening in the computational design, architectural and design, computational design, and on the other side in the biology. And if you don't trust me, this is a 4 years old image from the Autodesk website. Autodesk is working since years. The name of the project is called Project Cyborg, on some software in order to design and define the biological properties of the materials. Those are some plugins you can install on 3D Studio Max, on Blender, on Maya, all the computational graphics softwares in order to start to define the bioproperties of the materials. So this is another quote from a very interesting interview to Andrew Hessel. Andrew Hessel is a bioprogrammer leading the Autodesk research project. And he was saying every living thing on the planet uses the same operating system, uses the same programming language, from bacteria all the way to us, and everything in between. DNA is the program from the living things. So now we have a clear path from bits to atoms. You remember the famous MIT slogan, from bits to atoms, to biology. We actually are going responsible for every living things on the planet and choose what we want to create. Not survival of the fittest, but construction of the intended. But the next programming paradigm is life science. I have to shortcut a little bit because I'm in delay. And I want to go back to one of the previous images I showed to you. Do you remember the four fields that Joe Hito was using to define the future of the design? I would add another one, because in those four fields, we are missing the actors. Who is going to do that? And I think that robots and machines is another very important field of research that we need to start to use and to explore. We are witnessing the rise of computation as the design medium, and this is something that we already understand. But we also need to define how we do that and how we use our processes in order to inform the material. Robots are, I consider robots and machines as technologies that are able to execute instructions, series of instructions. So I'm not just thinking about 6-axis arms or something like that. We can range literally from very small robots to very big ones, and very different also in the topology and morphology itself. This is the new Tesla factory in Fremont, in California. And as you can see, the robots are widely used, but the robots are not in use since 40 years. The robots are really old in some way. It's a 40 years old technology, and obviously it's already in every automotive company, in aerospatial factories and so on. This is the daily shipping in Shanghai from KUKA, is one of the biggest companies all around the world. So in the next 2 years, just China is thinking to sell more than 2 million of robots. So you can imagine how robotics will be in some way pervasive in our world. But since I could say 10 years more or less, also architects and designers are starting to be interested in the use of this kind of technology in the architectural and design fields. This was one of the first, let's say, robotic performance I saw, made by an Austrian studio, Kram and Weiser, and it was about to cut some stools using an app where you define 3 curves, and the intersection of the 3 curves in the 3 directions of the stool will define the final shape. And in a few days, they were able to collect from different participants to the event very different shapes. So it was a way to show that robots were not that far from something that could be related to the design. But in the last years, obviously, if you are a little bit aware of what's going on around the world, robots are in some way going to fill every architectural school or design schools. But it's going also to happen in construction. This is a project made by Kopimmerblau about the mock-up Museum of Contemporary Art in Shenzhen, and the entire facade system is supposed to be built by robots. So basically the robots are delivering the material, placing the material in the exact position, drilling and fixing the panels on the facade, and then welding the facade itself. So the architects are starting to be used to not thinking about just to the material or the shape of the building in itself, but the processes to build and to use those kind of technology in the building site. This is another image from the supposed Google headquarters. And as you can see, the robots are not just robots anymore, but there is a sort of speciation of the robots. So robots that are going to be different because they have to solve different functions during the building process. So basically, there will be robots that will deliver the material, other ones that they were welding and doing different tasks. This is one of the most famous robotic pavilion in which robots were extensively used. And I really like to think at this pavilion as a sort of paradigm shift in the architectural design and processes. New generation of architects and designers are starting to be used to those kind of technology, to understand the language of the technology itself, and to start to use the technology in the building processes. I don't want to say in the building in itself, but we are talking about building processes. In this specific pavilion, for 1 year, the PhD students and the master students started to develop not just the shape that is inspired to some biomimetic properties, but to define the tools, to build the tools in itself, to define the materials, because they draw, literally, they design the materials that they used, and then the process in order to build the pavilion itself. So the students and the PhD students were able to define the entire process from the very first idea to the process, to the building process in itself. And this is something that is going further. I think one of the main bottlenecks that we have now in order to move from the research lab to the industries are in first the regulation of this kind of processes. It's very hard to move from a lab to the certification of the processes itself, but it's going to happen. It's just a matter of time, probably. Few companies are actually on the market, but the number will grow for sure. And they started to deliver this kind of additive manufacturing processes in the real building site world. This is another example, is very new one, is the MX 3D bridge made by this company. Basically, they 3D printed metals, and they 3D print the entire bridge in one piece, let's say. It's not exactly true, but a very big one. And there is a huge amount of research behind this project, not just in order to understand how the welding process that was used by the automotive industries until now could be useful in architecture, but how to use the robots in a completely different way. Because when you think about the robots in the automotive industry, they are doing the same operation 1 million of time. In this specific way, you are doing with the robots one specific operation each time. So everything will change in the control of the robots. You need a more faster way to approach the robot, to program the robot itself, and to use new tools all the time. So it's a very challenging project, but I think very successful. And this bridge will be put on the site in the next months. And one of the main difficulties will be how to certificate the bridge, because there are no technology and any kind of software that could certificate how this kind of new technology, new 3D printed object will work in the real world. So basically, it will be a sort of a test, a living test, full of sensors in order to understand how this technology will work. Then, obviously, we are also moving to the swarming robots. So when I talk about robots, it's not just big ones, but also very small ones that are working together, doing different tasks. This is a very interesting project by Mariel, where she was using a couple of those climbing robots in order to use those roads and to define some topology on the wall. Very interesting one. So we are moving, after many years of digital predominance in architectural research, to matter. And that's something I really like. I changed my approach to computation since we are working on the prototypes, and we are working with the robots and with the additive manufacturing processes. Because until you really reach the level or you reach the knowledge about the material and the processes and the tools, you can't really define which is the process that you need to use in order to define your project itself. So I want to leave you with some questions. In a world where technology and biology are becoming the new media, our ability to shape matter, to program matter is radically improving. Our tools are enhancing, and the fields of exploration and application are widening every day. Are we ready to be architects and designers? This is the question I'm doing to myself every day. Are we ready to cope with those huge technology changings that are happening? If intelligence is the ability to adapt to change, am I really intelligent? Sincerely, I don't know. That's all. Thank you. If you have questions, we can save the question for the last part. I leave the word to my colleague Marco Palma, that was my colleague during the last 2 years of research. So he will show you what we were doing in the last 2 years. Thank you. Maybe.
Tasca, mettiamo in tasca. Devo solo capire se...
Forse non nella presentazione, nella modalità. Scusa.
Ma l'hai spenta?
No, no, devi spostarlo nell'altro video.
Ok, allora aspetta.
Se riesci.
Aspetta, facciamo così. Cosa vuol dire
No,
nell'altro
accendi.
video? Sì.
Ok, buttalo nell'altra finestra davanti.
Ah, ok.
A destra, a sinistra.
Ok.
Esatto. Poi c'è. Devi solo allargarlo se c'è. Esatto, sì, sì.
Ok. Okay. So, can you hear me? Yeah. Good evening, everyone. I'm just showing you a quick video about what I'm going to talk about next. So please enjoy. Right, that's it. Thanks for your attention. This was just a quick preview, sneak preview of what actually was our path in the last couple of years of research in Torino, in our laboratory. I'm now presenting you these topics with a bit more of insight. If I actually find it, I'm sorry. Right, so in this part of the presentation, actually, I'm going to try to give you a brief insight of what actually is our perspective on things, starting from what Andrea was actually explaining to you before. And I'm going to try to summarize the work we have been doing in the last couple of years in the project which is called Digifactoring. First of all, Digifactoring is a collaborative project that started in March 2015 in Torino that sees the collaboration of different actors. Fab Lab Torino, which is the first Fab Lab ever founded in Italy. Officina Innesto, which is a spin-off of the company Arduino, which then relates to topics such as Internet of Things, physical computing, and digital fabrication. Then, of course, Codate, the computational design group co-founded by Andrea. Coma Robotics, which is a Turin-based, so Italian, robotic company, which is actually responsible for the automation part of Fiat Chrysler automobiles industrial lines. And Toolbox Coworking, which is actually a very, very nice space in Torino, which is providing us the space and the lively community of people. Somehow, all of these actors were converging around the idea of exploring a new disciplinary territory where industrial machine and robotics in particular are used in order to generate innovative contents in the broad area of creative disciplines. In particular, we like to think about Digifactoring as an independent applied research cluster. Independent meaning that we are not part of the university, but we are somehow self-funded. So a research cluster that works around the areas of computational design, robotic automation, material explorations and engineering, and digital fabrication. Starting from these ideas in October 2015, more or less, we took part to a call for projects that was aimed at supporting transdisciplinary ideas and in the areas of arts and technology. So we wrote a proposal, a project proposal called ARM, Algorithm, Art, Robot, and Material, that was aiming at somehow exploring the artistic potential of industrial robotics and additive manufacturing. And our precise goal was actually to produce a series of artifacts at the domestic scale. We were lucky enough to be shortlisted, and actually we got fully funded. That means that in 2 years, we were able to do many things. First of all, we actually used this financial support to activate a research and development program aimed at developing software and hardware solutions for additive manufacturing. And specifically, we actually focused our research lines into 4 different areas, each one of those was related to a specific material system, so to say. Clay and ceramics, thermoplastic polymers, biologic materials, and tension-active systems. We then, in order to test somehow the technology transfer and knowledge transfer of the investigated topics, we promoted 4 international workshops. One of those actually, each one of those was related to one of the 4 research lines. We activated 4 international residencies with 3 international residencies with 3 artists and researchers. Yanis Lallemand, a French PhD student from INSAD Paris. Francesca Perona, who's an interdisciplinary designer based in London. And Maurizio Montalti, who is a well-known designer working with biologics material based in Amsterdam. As a nice side effect of the project, actually, in the course of these 2 years, we got in touch with different companies that asked for our consultancies. In this way, we actually could test, once again, at another level, which was not actually only research or education, our technologies. Actually, as Andrea already mentioned this, but the focus of the talk today is actually going to be addressed to the practical and theoretical contribution that CODEIT could provide for the development of these research lines. The contribution actually is called inFORMed matter research, and it focuses on the exploration of additive fabrication processes in order to inform, in the sense of giving form to matter by taking advantage of its inherent and intrinsic morphological, morphogenetic, and self-organizational properties. In order to trigger these self-organizational properties of the material, like Andrea was mentioning, we actually use code. We use additional levels of information in our computational design tools in order to make the fabrication process something that becomes a full part of the design process. This means basically that the main research goal of the inFORMed matter research is actually a step beyond the state of prototyping, which thinks about a design as just a replicational phase, a fabrication, about, how can I say, the main goal is actually to step beyond the state of prototyping, according to which we think about the physical model as an exact copy of its digital counterpart. So we actually try to do something more. We try to use different informational levels in order to reinterpret the design process and the fabrication process. What does it mean? It means that we would like to get rid of this conceptual boundary according to which what we model on the computer and what we fabricate are exactly identical. So we would like to skip this idea of thinking in a linear fashion, where the product is the exact copy of what we were designing on the computer. What we would like to promote with this research is actually another approach, which is feedback-based. So we don't want to think anymore about the process of design as a linear one, but as a feedback-based one, so that actually the digital and the physical domains are exactly the same, and they are just two complementary instantiations of the same set of information. When we start thinking about in this framework, we actually start thinking about a system of elements that are actually influencing each other interdependently. That means that our setup is not just a computer, but is a system of components like a robot, the code, the material, and the end effector that constantly inform each other during the fabrication process and the design process. So let's say that every small change that is introduced in the system at every of these levels have an influence on the final physical outcome of what we're going to produce. In order to control such a system, we needed to develop tools to control it. So on the computational side, this is our tool in order to generate the amount of information that we need to talk with the system itself and with the machine. As you can see, it's a grasshopper definition embedded so in the rhinoceros environment. So we are actually working inside a 3D modeler, and we are inputting geometry. And what we are getting from this as an output is a set of informations that the robot can read and interpret, but not only the robot, also the tool that the robot is moving in the space, which is depositing or releasing the material. So it's a quite a complex setup, but that's actually fundamental in order to generate the informations that the robot and the fabrication setup needs in order to work. We developed, on the other hand, the end effectors, so let's say the hardware solutions in order to release different kinds of materials and to work with different kinds of materials. On the top part, you can see the clay extruder that we also use for the biologic material depositions. And on the bottom part, the thermoplastics extruder. By the way, all of these, both the software and the hardware solutions that we developed are free to download at our GitHub page, because part of the goal of the project was to make these technologies open and available for people to replicate such an experience. These tools are actually made out of very cheap components, off-the-shelf parts that you can easily find in any hardware store or on Amazon. The third component of our system is the material. And this image, I guess, is quite powerful because it actually expresses something that I at least particularly care about, which is the cooperation between machines and man. And this doesn't necessarily mean that the man is the one who is programming the machine, but in order to work with matter and with material, what's needed still, and that will still be needed in the future, is the knowledge and the sensibility and the sensitivities for the material, which is typical of the craftsmanship attitude to work. And it's something that very hardly is going to be replaceable by other form of intelligence, so to say. So we can directly jump into the 4 research branches that we were developing. The oldest and the first one I'm going to present you is called inFORMed clay matter. And somehow, when we think, if you look at these images, you actually may start thinking about something went wrong here. Yes, somehow, but that depends on the way we're actually thinking about errors and mistakes, because we often relate errors to some undesired deviation from our original plan. On the other hand, somehow, as designers and researchers, understanding which are the limitations of our control over a process through analysis, observation, and creative thinking may actually end up in positive results and innovation, maybe. That's what actually this picture is representing, because this was actually an attempt to print a very simple geometry, a cylinder. At some point, the structure couldn't hold its self-weight anymore. Something in the system was corrupted somehow, or the balance was broken. And during the deposition process, at some point, the printer somehow and the material couldn't find, again, the support below itself. This actually triggered a very interesting phenomenon, so that the material itself, which is fluid, it has a strong liquid phase, started to somehow express its own inner logics of flow and dynamism in terms of fluid dynamics somehow. And this actually resulted in from our first expectation, that was actually to generate something very simple, let emerge something really complex, really interesting in terms of expression. And probably the most interesting thing is that this geometry, or this artifact that resulted from this error, wasn't designed. It wasn't modeled in the sense that we are used to as architects and designers. This is not geometry. This was not drawn in Rhino. They were just circles, one on top of the other. But some other informations took over at some point and let this happen. So instead of just cleaning up and trying to do another circle, another cylinder, what we tried to do actually was better understanding what was going on there. So analyzing the causes and the effects of our system. So we figured out why this was happening, and in the next iteration of design and fabrication, we decided, or we actually managed to understand why these things happen. And you can see here, for example, it's quite clear, but the points where you see all these small bubbles or perturbations were due to a slower speed in the deposition process, while the more regular one were actually a higher speed and a lower layer height. So we could define exactly the points from the start where to generate these effects. So this is starting to be something different. Still is exploring some behavior, but it's not a mistake anymore. We actually went on with these explorations and tried to, little by little, organize them in some sort of way. We opened also our tools to students and to other researchers so that they could play in the same fashion that we were doing. And many different variations came up. Many explorations popped up. And let's say that this clay research went through many stages. One of those was the need somehow of categorizing all these behaviors, all these somehow new vocabularies that were emerging in our research. So we also wanted to stress somehow the concept of flexibility in terms of production possibilities that numerically controlled machines actually have. So when you are having a numerically controlled machine, you're not stuck anymore to the idea of identicality and replication, but you can actually design variations at the same cost as you could actually design identicality. The research went on up to the point of approaching these early explorations with some sort of clearer design intention in order to express our own somehow personal interpretation of the system potential. And we started to generate a sort of let's say, few series of objects as designers. This, for example, is called Gravity. It's a series of clay bodies which actually intentionally, during the fabrication process, the deposition starts to get out the boundaries. So the gravity and the self-weight of the material is actually self-organizing in this way. Or, for example, this other series that we called 6-axis, because this sort of material deposition is would not be possible with a standard 3D printer because it only moves on a vertical axis. By exploiting the full kinematic potential of the robot, we can actually start escaping from the vertical lines and the vertical extrusions, and we start to actually squeeze the material in different directions, also exploiting, of course, the softness, the soft properties of the material. This is another very interesting effect of our research, because instead of working with a standard circular nozzle, we started to work with, let's say, a 45-degree cut nozzle for pastry, basically. And actually, once again, all of these effects, which are extremely complex, extremely fascinating, are not modeled. They are just a self-organization of the material during the deposition process. The material starts to laminate according to the directionality of the nozzle during the printing process. The clay project actually, for a certain extent, could be considered almost concluded, in the sense that from these very early explorations that we showed you before, we actually arrived at the level of control of the whole process that we actually defined some pieces which could be considered almost products, almost reaching the product stage. So at some point we were trying also to sell them, but that became another kind of work, and we didn't actually want to pursue this for the moment. But if any one of you actually has good marketing skills, please contact us. All right, so then let's skip to the next research line. It's called Informed Polymers Matter. As you can imagine, it's about plastics, thermoplastics polymer. We were using the standard materials for desktop 3D printing, so PLA, ABS, PETG, polypropylene, and so on. And somehow on the other end of the spectrum from the clay project, this research line is more about control rather than flow, if you get what I mean. We actually started experimenting with this special and, I would say, non-standard way of using 3D printing technology. That means that we are not superimposing layers one on top of each other, but we are actually releasing materials in all direction of space. This process may look sort of simple, but you have to trust me, it involves a really high and deep level of control over the robotic movements, over the computational aspect of it, because every line that is drawn is actually informed with different properties, with different informations related both to speed of movement, quantity of material extruded, temperature, delay time in order to let the material cool down, so to move again and not to drag the material away while you are printing. Also, the same level of complexity has to be somehow mirrored in the extrusion phase, so in the tool side of things. So, as Andrea showed you before, these sort of structures are already somehow being engineered by more than one company, especially one is called Branch Technologies, and they are producing in the same fashion free-form space frame structures that are used to design and build partition walls. So they're actually getting in the real world as a technology. We also tackled standard 3D printing somehow by somehow trying to move away from desktop 3D printing in terms of scale and in terms of speed of production time. So basically, 3D printing is still at very low resolutions, like a standard desktop 3D printing. It requires a long time for fabrication. Since we are actually able to use quite a big machine as an industrial robot, it has like 2.3 meters of horizontal reach. We decided to try to print bigger and with lesser actually time, with much time saving. So here we designed a very somehow simple prototype of a table, and we also designed a series of suspension lamps in PET-G. The next research line is the one at probably at its earliest stage, also because of its inherent complexity. It's called inFORMed Biomatter, and it's a collaboration between Officina Corpuscoli or Maurizio Montalti, who, as I told you before, is a very well-known and expert designer who is working with biologic materials since almost 10 years. He's specialized particularly in the use of fungal species to design, basically, objects. This project was also interesting somehow for the European Space Agency, and I will later talk about it. The idea of this project is somehow simple, and it's about 3D printing robotically scaffoldings for fungi to grow. These images that you are looking at basically are expressing the material that just being deposited on the top part. It's a sort of very toothpaste-like material, so it's very soft, it's very sticky. But after 2 weeks, it completely changes its own mechanical and also aesthetical properties, and it turns out to become extremely lightweight and extremely stiff. Why? Because in this toothpaste, brownish toothpaste, are already inoculated spores, in this case of mycelium, which is a species of fungus which grows at the nanoscale in a sort of extremely dense network of cells, which has this look. Actually, it looks like the cheese you leave in the fridge for too long and you start to see this fur. Actually, these are hyphal cells, which are actually the main constituent of fungi. This extremely dense network is permeating the whole paste that we were printing, because this paste was filled by nutrients, which is basically cellulose, which is the main ingredient and the main food for fungus. The biggest part of the research is actually related to the material definition and the material engineering in order to make a living organism to be extruded with a robot. It's not easy because it requires a lot of fine-tuning, a lot of atoms, a lot of knowledge, also in terms of how to handle the material, where to make your tests. You need a sterile environment, otherwise the fungi are dying or are getting rotten somehow. So with Maurizio Montalti, we ran a workshop, one of the workshops, and it was very successful in terms of participation. Many students came, and we divided them into groups in order to test with different kind of fungi, with different kind of binders, with different kind of receipts in order to develop their own, let's say, recipe, for the extrusion of mycelia. I was mentioning that also the European Space Agency got interested in this technology, because basically, if you think about a mission to another planet, most of the costs are to cover the travel somehow. So you don't want to, if you want to build some structures on Mars, you don't want to bring with you tons of bricks. So you want to bring the people and maybe some machine and maybe some food, but you cannot afford to fill your spaceship with bricks. So ESA got extremely interested in this possibility of growing your own construction material on site, because basically cellulose is just a waste product. So it's wood dust, wood chips. It's a very cheap material. And you can actually, and fungi and the spores of mycelium are, you can just bring them in a small plastic bag, a few grams. So that's why, let's say, the advanced concept team of ESA is extremely interested in this sort of technology. We hope to continue to push this research with Maurizio Montalti and, of course, with ESA, because it's extremely interesting form of design as well, because you're actually printing, you're actually designing something that changes its properties over time. So, you know, the role of the designer is really put into discussion. You're not actually creating a shape that has to be like this, but you're actually designing the framework around which the product is going to develop in the very sense of the term, since it's actually living. We could talk more, but I guess I'm already late. I move a bit faster to the last research line that we were developing into digifactoring. We called it inFORMed flexible matter. We did it in collaboration also with WASP. Many of you may have known about them and about their technology for 3D printing. And you may also have seen something similar coming from the MIT Self-Assembly Lab with a project called Programmable Textiles. The idea is quite simple, yet very difficult to actually simulate at the computer. What happens? It happens that it's a double material tension active system. To be very pragmatic, what you need is actually to take a piece of fabric, a stretchable fabric, like Lycra, you put in pre-tension over a frame, so you actually store potential energy. While the fabric is in tension, you deposit material who adheres to the fibers and actually fills the gap in between the layer and the mesh of the fabric that you're printing on. And this acts basically as a constraint, as a physical constraint, so that when you are releasing the tensions of the fabric, depending on the geometry that you were printing on top of it, the shape, the fabric starts from a two-dimensional configuration to assume a three-dimensional configuration. These, just like somehow the clay is not known in advance, the effects of this system is not known, or it's very extremely difficult and computationally expensive to simulate. That's why it's a very engaging and funny, actually, project to follow. It's very useful also, this is just my opinion, but in terms of teaching students what are the consequences of their drawings, somehow. And this actually triggers an immediate feedback loop in the design process, because you draw something, you test it very quickly because it's an extremely quick process. You go back and you try to adjust it according to your design intentions. Or maybe you just follow the material behavior in order to explore some new possibilities. We did a workshop with 10, 15 students, and in 3 days we produced more than 150 samples. And since, let's say, the aim of our research project was to design some house and domestic scale objects, we decided to take the experience of the workshop and in 3 days design some suspension lamps. I guess I'm over, and I would just like to thank you once again and to remind you that if you are interested in more informations, we recently released a free publication. You can check our websites and Facebook pages. It's a quite exhaustive, extensive publication, and that's it. That's us. Thank you very much for having us once again and for your attention. If you have any questions, we are here.
No,
it's okay, it's okay.
Obviously, the first advantage is that you need to take with you in a space mission very few amount of material. Because cellulose will be provided from any culture. If you need to eat, you need vegetables, so you have some cellulose in some way, and you can use the discarded material from the food as nutrients for the fungi. So basically, you are lowering the cost of the mission a lot. Then it's a very strong material. As you can see, after 2 weeks, you have a very light material because basically the mycelium are eating the cellulose and then the material is drying. So the weight of the material is really changing and lowering a lot, and it's very stiff. So it's light and stiff, and you can have it for free in some way. So that's the huge advantage in order to use this kind of materials.
On the other hand, I mean, on Earth, they also might have advantages, actually, not only in terms of, let's say, performance, mechanical performances, but mostly they are fully biodegradable materials with zero impact on carbon footprint somehow. So that's what most of the designers, product designers, are shifting to these sort of materials in order to actually stop the plastic production that is actually affecting heavily the ecosystem of the planet. So, or they might have several other uses, like always in terms of replacing plastics or petrol-derived materials for packaging or for other sort of uses like bags, shopping bags. Of course, other people is experimenting with mycelium for construction, since it has a very good compression load-bearing capabilities. So there are many experiments also in the architectural realm, so to say.
Also in fashion design, actually there are some designers that are starting to use fungal species in order to build textiles in a very successful way. So you can substitute, leather in order to build some fashion dresses. So very interesting. Next one. Yeah.
What's the impact on how much time it gets to keep the properties intact of
The myceliums? I would say in a couple of weeks, if you stick to the protocols, you completely transform the material. Obviously, it depends on the size and the amount of material you're releasing. They are starting to colonize the surface because it's easier in some way, and then they start to grow inside. So if you have a very thick object, probably it takes more. But the samples that we did in a couple of weeks, they were 50% colonized. So
when they finish the food, they just stop the process.
Obviously, something that we didn't say, but if you want to stop the process, you just need to eat the object a little bit more, because if you exceed the, let's say, the basic temperature where they grow, you are killing the living parts of the material.
You can make them grow, make them grow bigger, like even food before the rating.
Sorry, I didn't.
You can make them grow more, give them food.
Yeah.
And feed them before the printing, so they can grow bigger.
I would say when we print them, they are already colonizing the cellulose. We are just breaking the connection in order to make, again, a sort of toothpaste material. So the cellulose is already, I would say, heavily colonized by the mycelium. So it's just a matter to have a printable material that rebuilds itself in a few days. So everyone is interested by mycelium. No, it's true. Keep in mind that IKEA just opened a new department in order to use mycelium, these kind of techniques, in order to replace the packaging for in the next years. So it's something that is going to heavily use.
Andrea?
Yes.
You also talked about the
research that we did completely changed our attitude in terms of thinking about the final product. We are not thinking about the final product anymore. During the workshop, we had the confirmation that basically after 3 days, all the participants started to think about the design in terms of information. So just information, it's completely unuseful to draw beautiful, smooth surfaces or meshes when the robots want just points, speed, and the tools just want temperature and whatever. So you just need to design those kind of information. So we did a show, but the models basically are points colored by different set of information. That is already a sort of visualization, data visualization of the code that we are providing to the system. And that's something that really changes your attitude to the design. I would say we start from errors, and we just presented in Paris during a lecture. Basically, what we are doing is really hard to simulate. And so if you can't simulate, what about precision? Because the precision is the gap that you have from the digital model and the real one. But you see, if you can simulate it, you can't measure your precision. So this is a very interesting topic. One of the next conferences will be about imprecision. I don't remember which one. And I think it's a new topic that we have to explore. We are not going to design any final product anymore. We are talking about processes, endless processes. This is another very interesting. We can go with the same research for 10 years and every day explore something new and discover something new. So it's something that never ends. You just have to stop because you have to do something else. This is another very interesting point. So you are stressed by the, to reach a point usually. In that way, you start to be acquired, to be confident with the fact that you can never stop something. You can go deeper and deeper until you die. Someone else?